Okay, turning to the top of page 23, we have the second half of electrochemistry. And this is where you can really see where the word comes from, because we're using chemistry here to either generate electricity or using electricity to force a chemical reaction to occur. So there are two types of electrochemical cells. The first type, on the top half of this page, is called a voltaic or galvanic cell. Voltaic is the most common reference to it. All right, and in a voltaic cell, we're producing electricity from a spontaneous reaction. So all we have to do is bring these components together, and the electricity is going to flow on its own from the more active metal to the less active metal. We're producing electricity, as opposed to the second type of electrochemical cell, the electrolytic, where we're using electricity. And since we're producing electricity here, what we say is chemical energy or potential energy that's stored in the reactants is converted to electrical energy. Okay, so in a typical setup, what you would have is two pieces of metal, electrodes, in solutions of their ions. So the zinc is going to be in a solution of zinc ion with a sulfate or some other polyatomic like a nitrate that won't interfere. And the copper is going to be a solution of its ion, copper sulfate in this example. I just used sulfates, but you could have used nitrates or whatever. But this is the classic setup. And the reason why we place the metal in a solution of its own ion is because it won't react with itself, and the copper won't react with the copper plus 2. So the reaction is really between the zinc and the copper. The first thing you have to do is you have to determine, using table J, which is the more active of the two metals. So when you go to table J, you'll see that the zinc is above the copper. Therefore, the zinc is more active, more willing to give up electrons. All right, so the more active metal will be the anode. The anode. That would be the zinc in this case. And since the more active metal is the anode, the less active metal would be just the opposite, the cathode. Okay? Now, what occurs at each of these electrodes? Well, if you remember, an ox and a red cat. That will say it all. Anode, oxidation. All right, cathode, reduction. So we call these pieces of metals anode and cathode depending upon whether oxidation or reduction is occurring. All right, and since the zinc is the more active metal, that's the anode where oxidation takes place. And so electrons are going to go from the zinc towards the copper, from the more active to the less active metal. In the process, as electrons are moving from the more active to the less active metal, then you could register the voltage behind that with a voltmeter. That's what this would be. Or in line with this, you could place a little light bulb or something like that, and it would light, provided it could light with the small voltage that this setup actually gives you. This only gives you about 1 point something volts. Anyway, so then the zinc being the anode, being the source of electrons, let's put little E minuses there for that, all right, would be the electrode that is labeled negative. Okay? And the electrode where the electrons are going to, the cathode, in this case, the voltaic cell would be labeled a positive. Now what's going to happen over time is, because the zinc is undergoing oxidation, as you can tell from this half reaction here, all right, we're going to divide this total or net reaction into two parts. The zinc is going to undergo oxidation. Here are the electrons that are going to be conducted through the wire. And then on the other end, the copper plus 2 is going to accept those electrons and form copper 0. So since the zinc electrode is undergoing oxidation, over time, this electrode is going to get thinner. It's going to oxidize. And the copper, on the other hand, since you're forming copper metal, this electrode is going to get fatter. It's going to increase in mass as time passes. Now, the salt bridge here, which is an easy way to tell the voltaic cell apart from the electrolytic, if you see below. In the salt bridge, what we have is the conduction of ions. So in here, ions flow. Now, you really don't have to know the direction in which these ions flow, but just for the purposes of completing this idea, since electrons in this case are traveling this way, they're traveling clockwise, if you will. All right, to complete the circuit then, the electrons have to travel, or the negative charge, better said, has to travel by way of ions in the salt bridge that way, to continue that flow of negative charge. So the negative charge by way of electrons in the wires, and the negative charge by way of negative ions in the salt bridge. The whole point of this flow of ions is to maintain an electrical neutrality. You want to keep these half cells electrically neutral. So ions flow to keep the half cells electrically neutral. All right? And so again, electrons are conducted in the wire. Let's highlight that. And ions flow in the salt bridge. The anode loses mass. The anode in this case would be the zinc, the more active metal. And the cathode gains mass. The cathode in this case would be the copper, which is the less active metal. And here you have your half reactions that break it down into two parts. So again, in the voltaic, notice the anode is negative. In the voltaic again, the cathode is positive. All right, and we'll do some problems with this as soon as we walk through the electrolytic cell. Continue. Now the electrolytic cell, right away you can tell is very different in appearance from the voltaic cell, because in the electrolytic cell you'll see a big battery. We're using a battery. We're using electricity to make a reaction that is non-spontaneous, to force that reaction to occur. So here in the electrolytic, we're using electricity. And so we're doing the opposite of what we do in the voltaic cell, which is that electrical energy is being converted to chemical energy. All right? Now, there are two applications of the electrolytic cell. One is electrolysis, where you're using electricity to quote-unquote split a compound, and the other one is electroplating, which we'll talk about in a second. All right? So electrolysis, electricity, lysis is split. You're splitting a compound. Right? The compound in this case that we're quote-unquote splitting, that we're breaking down chemically with electricity, better said, would be NaCl. So if you recall, when we did periodic table, I mentioned that the way to extract the group 1 metals from their compounds is with electrolysis. All right, so if we take sodium chloride and place it in this tank here, so this tank contains molten NaCl. It's in a liquid state. And we have these two electrodes inside this tank. This happens to be very hot. Remember, sodium chloride has a melting point of 801 degrees Celsius. So this isn't something that we would demonstrate in class. The first thing you should do is follow the battery terminals here. The negative would make this electrode negative. The positive would make this electrode positive. And again, notice electrons are coming out of the negative electrode, and electrons are returning back to the positive electrode. All right, so now think of electrons coming out of here and being available at this electrode. The electrodes in this example do not participate. They have nothing to do with the chemical reaction. They're just conducting electricity. So think of this electrode, even though it has a technical name, think of this electrode as an electron gun, as a friend of mine used to put it. All right, so this electrode, since electrons are being forced out of the battery, is shooting electrons at whatever is attracted to it. And what's attracted to the electron gun, or the negative electrode, is the positive ions here. Because remember, when you have NaCl liquid, when it's melted, the ions are no longer attached to each other. So they're free to move. And so the positive ions will be attracted to the negative electrode. And what we're going to see over time is that those sodium ions are going to be reduced and plate that negative electrode. So at this negative electrode, since the sodium ions are gaining electrons, which is a reduction, we call this electrode the cathode. So the cathode in the electrolytic cell is the negative one, which is the opposite of the cell we just covered, the voltaic cell. So here's the half reaction. The sodium ions, which were in the molten NaCl, grabbing electrons or accepting electrons from the battery, forming Na0. So we'll make that fuzzy to remind you it's going to plate the negative electrode. Then on the other end, there has to be a return of electrons. So this electrode here, the positive one, is going to grab electrons. Instead of shooting electrons, it's going to grab electrons from whatever is attracted to it. So we'll call this electrode here the electron grabber. So when the chloride ions, since opposites attract, are attracted to the positive electrode here, what we're going to see is bubbles coming out of this molten NaCl. And those are bubbles of chlorine gas, because the chloride ions are going to be forced to give up their electrons, and the chloride ions are going to form Cl2. So we have here an oxidation occurring. And so since the oxidation is occurring at the positive electrode, we name this electrode the anode, since we said from the beginning, an oxygen or red cat. At the anode is where oxidation occurs, but the difference here is that it's positively charged. All right? So again, the electrodes don't react in this setup. They just conduct electricity. All right? The DC here, by the way, stands for direct current. All right? Just to remind you that you need a source of direct current where the negative stays negative throughout the whole experiment. The other kind of current would be alternating current, which you would get from your outlet. All right, you need direct current here for this to work. Okay, now let's see the second application of the electrolytic cell, and that is electroplating. And you want to plate one metal with another. And that's just below this one. So the second type of electrolytic cell is used for electroplating. All right, electroplating is, again, using electricity. We're using electricity always in an electrolytic cell to plate one metal with another. To plate means to cover one metal with another. So suppose you wanted to plate this fork here with copper, or with gold or silver. So what you would do is, again, to follow the terminals of the battery, the negative terminal is what you would connect the fork to, which would be negative. The positive terminal is what you would connect the piece of copper to. So electrons are coming out of here to your electron gun, and electrons are coming here for your grabber, if you will, returning to the battery. But in this case here, unlike the electrolysis, all right, the copper electrode actually is undergoing a change. You'll see over time this copper electrode begin to get smaller and smaller. Because what's going to happen is, as this copper gets oxidized, all right, and forms copper ions that go into solution, then those copper ions are going to get reduced by the fork and end up plating, as they form copper metal, the fork. All right, let's go through that again. So inside here, you're going to need a solution that contains the positive ion of whatever metal you're using. So copper, use copper sulfate because it contains copper plus 2 here. If you wanted to plate with gold, you'd use gold ion, Au plus 3. If you wanted to plate with silver, you'd use silver ion, Ag plus. But I use copper here in this illustration because I demonstrated this one in class with my students. All right, and I plated a fork with copper. So again, at the anode here, which is the positive electrode, we're going to have oxidation occurring, an ox, and a red cat at the cathode, which is the negative electrode. We're going to have a reduction occurring. And if you look at these two reactions, these half reactions, you'll notice they're the complete opposite of each other. So here you have the copper, from the copper electrode being oxidized, and copper ions going into solution. And of course, electrons being drawn back to the battery. And then you have on the opposite side, the copper ions that come out of solution, gaining those electrons that are coming from the battery and forming copper metal. All right, and so that is the plating that occurs. All right, in this case, the negative pole, just as in the opposite, even though the plating really isn't the point of the not the opposite, but the electrolysis. All right, the negative pole here gets plated with free metal. And what I mean is, once again, in case I confused you, the negative pole here is the fork, and the negative pole in the previous cell for electrolysis, negative pole connected to the negative terminal was this one, and it got plated with sodium, even though that really wasn't the purpose. All right, it wasn't. Our intention was not to take this electrode now, plate it with sodium, and use it for something. No, we would just scrape off the sodium, which is now free metal, and then use that for some experiment. Okay, so the negative pole in the electrolytic cell, whether it be electrolysis or electroplating, the negative pole gets plated. Now, another thing you want to note here, in both of these cells, it is an ox and a red cat. It is anode oxidation, cathode reduction, except the signs are reversed. So in the voltaic cell, look up above, look at your notes, in the voltaic cell, once again, the negative electrode in the voltaic cell is the zinc, the more active metal, which is the anode. All right? But in the electrolytic cell, the negative electrode, where in this case here, reduction is going on, is the cathode. Okay? So it's an ox and a red cat. Anode will always be where oxidation occurs. Cathode will always be where reduction occurs, but the signs are reversed. Okay, that's good for our coverage of electrochemistry. Let's make sure we do some questions now. So you can go over the notes, take a break, and I'll see you later when we do the questions.